Let's do another example involving weights of dogs. So again, we're supposing that the weight of a breed of dog is normally distributed with a mean of 17.5 pounds and a standard deviation of 3 pounds. Now this says, suppose dogs of this breed who are in the lowest 20% of weights are put on a special protein diet. What weight would be the cutoff for this diet? So in essence, we're asking what is the weight that cuts off the bottom 20% of the dogs in this breed. So the bottom 20% is, in our picture, something like that. Okay, now the first thing we need to find is the z-score that goes with that. So our z-score is going to use the inverse, or require the inverse norm button. So inverse norm, and this time, again, the inverse norm button always returns area to the left. So it always corresponds to area to the left. I'm going to put in 0.20 this time. And if you do that, you get negative 0.842. Now you should reflect on why that makes sense. Does it make sense we'd get a negative z-score there? Well, yeah, because the mean cuts off the bottom 50% of the data, right? The mean cuts off the bottom 50% of the data. So therefore, if you are cutting off the bottom 20%, then you're below the mean, and that just means your z-score must be negative. So we've got our z-score, but we've got to now convert that to a weight for this dog. So we remember this relationship. And again, I should have defined my variable. Let x equal the weight of dog. So z would be the data value minus the mean divided by the standard deviation. In our case, we know that. And we don't know the actual weight that goes with that z-score, but we do know the mean of this population of dog, and we know the standard deviation. So using a little algebra, and I guess, if you're like in my class watching this, I don't care about you don't need to show your work for this. You can just do this on your calculator. So we need to do negative 0.842. We need to times by 3 to undo that division, and then we need to add 17.5, and that tells me that the weight is 14.974. Okay, then it makes sense that that number is below the mean, okay, because our z-score was below the mean, indicated by a negative value. And also the bottom 20%, that number should correspond to a number that's below the mean. So the answer to this question would be 14.974 pounds is the cutoff for this diet. So it looks like if your dog weighs anything less than this, they're going to be put on the special diet. And if they weigh more than it, they won't. I wouldn't get too bogged down in the question, what if they weigh exactly that? Because we're dealing with a model here, right? And so that's just kind of it's a question that's going to lead you down a rabbit hole not worth considering. I mean, we're talking about a large number of dogs, and that would just be a judgment call, I guess, on the part of the dietitians or something. So don't lose sleep over that question. We're sort of blurring the line here in terms of what these percentages mean overall. But again, because the normal distribution is just a model. In any case, yet another example of using the inverse norm button. We're given a percentile, and we have to find the data value that corresponds with it. Here's one more example of using the inverse norm button on the calculator. Same context involving our breed of dogs. Now, this one's a little more applied because here we're told that, again, same distribution of dogs, the mean of the weight of this breed of dog is 17.5 pounds. The standard deviation is 3 pounds. This says the middle 50% of dog weights is between what two weights? So the middle 50%, by the way, that's that length, the distance between the two values that correspond to the middle 50% happens to be called the interquartile range, just to point that out. But that's like relates to a different concept. The middle 50% would look something like this, right? So there are two numbers that go here and here that create area in the middle that is 50%. So in order to find the weights of dogs in this particular context that create that, we first need to find the z-score that goes with this and the z-score that goes with this. Then we'll convert those z-scores into weights. Now the thing to point out is by symmetry of the bell curve, we know that once we find this first z-score, it should be negative because it's below the mean. But by symmetry, z2 is going to be the positive version of that. And I'll confirm that by doing it on the calculator for you, but you should just note that will happen. So let's find the z-score for z1. So we need to punch in inverse norm. Now let's look at this diagram. Z1 cuts off the bottom what? Well, if the whole middle is 50%, that means each tail here should be 25%. So I need to punch in inverse norm of 0.25. And when you do that, you get negative 0.674. Now I'm just going to claim right now that that is going to be, or that's going to tell us what Z2 should be, except it would be positive. But just to remind you, or just as a, an exercise in analyzing this picture, the thing you would have to punch in, if you didn't notice that, is, well, just think, what percentage is to the left of Z2? Well, there's all the blue, and then there's all this black here. So that's 75%. So you'd have to punch this in. And, of course, when you do that, you'll notice, as I'm doing now, you're just going to get the same thing as I claimed. Okay. Don't forget, though, we have to convert these now to weights, because that's what the problem's about. So let's convert Z1 to a weight. So Z1, remember, so the weight that goes with Z1 we'll call X1. The weight that goes with Z2 we'll call X2. So again, X is the weight of dogs. So Z1 would be X1 minus the mean divided by the standard deviation. So that means that Z1, which we found was negative 0.674, equals that weight that goes with it minus 17.5 divided by the standard deviation. Let's get the other one set up and we'll just do them both on the calculator. Z2 would be the weight of that other cutoff minus the mean divided by the standard deviation, which becomes this equation. Now let's just solve these both right now in one bell swoop. So I'm going to do negative 0.674 times that by 3 and then add 17.5 and I get 15.478. And then I'm just going to do 0.674 times 3 plus 17.5 and I get 19.522. Okay, so it turns out that, just to finish up and answer, So as it turns out, the middle 50% of dog weights is between 15.478 pounds and 19.522 pounds. I don't know why I decided not to abbreviate their pounds, but whatever. Cool, so that one was just, it's kind of a lot of concepts you need to put together, but just in general, we needed to draw the diagram correctly. We needed to punch the right things into the calculator to get those z-scores. We needed to know that we're getting 2 z-scores, and we needed to convert each of those z-scores to actual values that relate to the context of the problem. So a lot of moving parts here, but hopefully with some practice, you'll get fluent with this stuff.